In clinical practice, the Osiris Aberometer is, this instrument is a real mastering technology. You've just seen the features. I would point, besides the range, which is pretty big of measurement you can have, especially the resolution, the spatial resolution is really impressive. And as well as its temporal resolution, so that we can have real-time measurements. But for me, it's, as a clinician, is really a master in explaining things, in explaining the optics of the eye, of the patient that I have in front of me. We can, basically what we can do is measure the optical quality of the eye. We can measure the separate low-order aberrations, quantify them, higher-order aberration, then reconstruct a model of how the eye works optically with the PSF, the point spread function we are going to see, and most of you are probably familiar with it. And then via convolution of this information, we can simulate the visual effect, for example, on an optotype. We can detect and explain irregularities of the optics. We talk irregular astigmatism when something is different from spherical correction, cylindrical correction, and the optics are not working, for example, keratoconus. We were used to talk about irregular astigmatism. That doesn't mean much, but can be more detailed thanks to aberometry. But also other opacities like microfolds, capsular opacities, opacities of the IOL, or just cataract can be very well seen with this instrument. We can also predict the optical behavior of the eye, simulating what happens when we take away from the sum of the aberration. We can split the correction in. We can analyze also, this is something new, very useful, and I think Francesco is going to talk about this later on the IOL session, but I will anticipate this a little. We can study very well refractive IOL, and it's very important because nowadays we are using more and more of this refractive multifocal EDOF, extended depth of field IOL. So for the distributors, this is a huge potential market, but for us clinicians is great being able to see objectively these optical effects. When we then can integrate the aberometer with a topographer like a MES59 or the Sirius, or even altogether with the Osiris T instrument, we can separate and have together, but combine the effect of the corneal aberration with the total eye aberration, and then so by subtraction know everything about the internal aberrations of the eye. This is extremely useful when we are dealing with toric IOLs, and especially when we are not satisfied with the results, to check and adjust them. And then the dynamic measurement we've just seen from one of the last slides by Francesco, we can explore even accommodation, which is a pretty fast phenomenon. This is an example just to familiarize with one of the main windows that we can deal with when we're using the instrument. This is the visual effects. And we see on the right panel, I think you can appreciate that the retroillumination picture, the IOL in there as something strange that is a VVT, an Alcon VVT IOL, so has different concentric refractive areas. But also we can see this opaque line, that those are little faults in the capsule. They're not a major issue. In fact, you can see on the panel on the left, below the PSF, the point spread function, a point of an object should be a point in an image in an ideal system. It never happens, but we get pretty close to that if the optics are good. Here is pretty good. In fact, the simulation you see of the optotype also pretty small letters can be seen, but nevertheless, you see the refractive error map in color on top, and you see how the folds interfere anywhere with the image and with the formation of the image. This is another next example, very simple, is the first window we have. On the left side, you have the wavefront maps. On the right side, you have the refractive maps. Focus on the lower panel on the left. It's split it in two. One is on the left is the low order aberration. That is, we talk sphere and cylinder. On the right is the high order aberration. As you can see, on the right is almost all green. That means high order aberration are low. So we expect we can correct this eye easily. We go to the same window we were before, so the visual effects of the aberrations. And this is something strange. In the left, we cannot see really the point spread function. The PSF is so big that it fills completely all the field. But if we switch to a smaller pupil, a 3 millimeter pupil, we start seeing something. It's a circle. In fact, actually, you see on the right, there is a Zernike pyramid that splits the aberrations in all the components. And you see, I cancelled the cylindrical aberrations. So only the sphere is left, which is pretty bad. In fact, the optotype is barely visible. If we, on the other hand, cancel just the spherical error, things are better. The astigmatism is remaining. Looking at the PSF, in which part of the Strum's conoid do you think we are staying right now? We are just in the middle. It's the least confusion area of the Strum's conoid. If we correct all the first order aberrations, you see the red crosses on the right, we get a beautiful PSF and a beautiful ability to visualize the optotype. A very nice feature that I use a lot of this instrument, of the software of the instrument, is being able to obtain a similar effect in a more interactive and familiar way for us. That is, using lenses. You see on the right, there is a cylinder and sphere, and we can play with those and manipulate. And actually, if you click the BCVA, Best Corrected Visual Acuity button, the software is going to do the work for you. And I find when I'm not finding an easy solution with the usual autorefractometer that the optometrist is using, going to this one, usually we get a better idea what is the best possible correction, and we get some surprises. But the result you see is like before, the PSF is very good, vision is very good. This is, to me, is beautiful. If everybody, all of us have studied optics and imagined how the focus lines are at the extremities of the Strum's conoid, but here we can actually see them in the real eye of the patient. So this is one. We go to the other extremity of the Strum's conoid, we get the perpendicular one. And this is not just something playful for us, which is nice, I like it, but also with patients it's very useful. So we can show them what is the effect on visual acuity of this distortion. And in counseling, for example, for toric IOLs is extremely useful tool. This is an eye with keratoconus, advanced keratoconus. You see on the left lower panel, also the high order aberrations are pretty high. The coma is pretty apparent there. This vertical split in two parts, typical of keratoconus. And the optical effects of this, of course, are major. This is the PSF with a 3 millimeter pupil. It's just terrible. But the larger letters are barely visible. If we correct only sphere and cylinder, things are a little better, but still this kind of tail that's typical of the coma aberration is major and disturbing. And if we select the correction of the just the coma aberration, things are much, much better, even if this keratoconus is pretty advanced. With an advanced with a keratoconus that is not so advanced, we can get better results just without correction. With correction on sphere and cylinder, we get even a better result, but still you see the effect of the coma and the other aberrations. And if we correct them, we see how well the acuity can improve. This is another case of ectasia. It's a different disease. It's pellucid marginal degeneration. This is very interesting for us to analyze the effect of the different aberration, and particularly how in the center of the eye, of the pupil, the high order aberrations are not that big. This is the quality of vision we get, and by just correcting this cylinder mainly, we get beautiful results in PSF and visual acuity. This is important because these patients, sometimes one can think, well, we must go before undergo a corneal transplant, then we think about something else. Rather, as the aberrations are low order aberrations mainly, we can go on with the toric, ICL, or IOL, depending on the age of the patient and the situation. This is another case that looks pretty bad. You see how terrible the circles of the placido disc are. It's due to, this is an old radial keratotomy. But if we go to the quality of vision, optical, the central aberrations are not that terrible, and just by correcting with the sphere cylinder, quite unexpectedly, we get a very good result. In fact, the ideal of such a patient who is not that young, nobody is so young, if he has undergone the radiokeratotomy, he can improve very well his vision without touching the cornea, because touching the cornea in these eyes is a nightmare. With the premium IOLs, there is this nice feature of the defocus curve, an objective one. You can see here, this is the PSF and the aberration of null convivity. On the right, on top, this is a monofocal situation, ideal. You see the graph on the right is very steep. That is the focusing of the eye is centered at zero, that is distance. It goes down sharply on the right where the myopic steps are. It's -1, -2, -3, and so forth. But already -1, the acuity is very bad. In this case, here was the monofocality coming down here. Here, the focus in the visual acuity that you find is a simulation, of course, of visual acuity and estimation. The visual acuity is here. You see it's very high at zero distance, but it stays pretty good down to -1, that is 1 meter, and even pretty good at -1.5 diopters. So this is a good result for an aid of extended depth of field IOL. And this is pretty reproducible in other lenses, other patients. We see this broad peak in that area that gives good visual results. And this is just to show that you can select here the wavefront map or the refractive error map. With the refractive error map, the anatomy, let's say, of the IOL can be very well appreciated. This is another IOL. by another company, still a EDOF, maybe less extended, but with a little better distance contrast. It's another case with better extension. And this is another EDOF lens by Bausch & Lomb, where in this case the extension in the near was pretty bad, and also the patient was quite unhappy about it. What about the diffractive IOLs? This probably Francesco will explain afterwards why with diffraction all these optical analyses are more difficult. You can see the pattern here in retroillumination of the IOL, and the PSF is pretty good, and also we attempt to look at the focus curve, which is pretty extended. Another, actually, the main reason why Aberometry have been developed for eye care was to make so-called perfect vision, correct all the aberrations of the eye, so that we have the supervision. 2010 for everybody was an advertisement at the time. This actually is not done regularly, we all know, but there are platforms where the implementation of the aberometry can be transferred to the design of ablation pattern in order to correct aberrations. And this is an interface between the software from the aberometer and the software of the laser. This is an example of what we can imagine as a simulation of a treatment by, you see on the right that several aberrations have been crossed out, and we expect an improvement in the PSF and an improvement in vision, in acuity. And actually, this is the actual pre and post laser data. The improvement was there. The other, very quickly, the other point that we are using aberometry a lot combined with the topography is toric IOLs. In this case, you have left panel is total eye aberrations, center cornea. The right, that is derived as a subtraction from the other two, is the inner. You can see if you take a look at the center and the right, you see that the corrections are just one orthogonal to the other. So there is a very good correction of the IOL. Altogether, it's not a great aberometry though, because this is a very aberrated eye because of very old penetrating keratoplasty. But with this correction, the visual acuity was more than acceptable for the patient. In this other is just an example that the software can help us in correcting when something is not corrected. You see, again, center and right, you see that the two astigmatic patterns are not orthogonal, and so the astigmatism is by far not corrected. Actually, in the red square, the astigmatism is 14 diopters right now, but the software is helping us and tells that we are rotating the IOL, we can go down to about 2 diopters of astigmatism. The last thing is the dynamic aberometry that is fantastic. There is a target inside there is a special software in the instrument, and it drives a target that can be focused dynamically at different distances. And in this case, I try to show the red line is the change in diopters you see here of the target. So this goes near by 8 diopters. And this is the spherical adaptation in real time. You see how many points we have. We can even check how fast the accommodation is. And this accommodation goes down, up. And the green line is the pupil. As we, of course, expect, it constricts when we accommodate, and it keeps doing that. There is a second possibility, that's a staircase. You see the accommodation goes in step, the stimulus, up to 7 diopters, and you see here this 30-year-old patient could keep up to, let's say, 7, then it was enough. You couldn't anymore. So, in conclusion, the Osiris is to me a real master. It can help us in understand many things and making decisions. So thank you to Osiris, and thank you to you all for your attention. Thanks.